So again, this study was actually presented for the first time. This is only the second public display of this particular study. The first one again was at the National Pavement Marking Committee in Louisville, Kentucky at ATSA. So it kind of all starts with a call, and kind of like a lot of things, it starts with a call. I got a call from our retroreflectivity technologies product manager. Sounds special. He is special. He does a great job for us. And he begins to tell me that he has a puzzling issue. And he says, hey, we got some mobile readings. You see, we have a customer in Texas, and he's a pavement marking contractor, and he was using our LLG7 mobile retroreflectometer. And he says, well, while he was measuring the double yellow center lines, they found that the left line was reading lower than the right. So, me with my complete confidence in the LLG7, I replied, well, then that must mean that the left line was lower than the right. And so my mind already flipping through thousands of mental files trying to figure out, okay, what could be the possible cause? Was it material or application causes, that kind of thing? But that thought process was rudely interrupted because then he said, but when they turned the vehicle around and measured the same two lines in the opposite direction, the left line was still lower than the right. Well, it takes me a couple seconds to understand what he just said, but wait a minute. The line on the left going is the line on the right coming back. So how did that line go from being the lower to being the higher of the two? To add to our little puzzle that we had here, he also said that when the contractor used a handheld device, the measurements of the two lines were nearly identical. I thought, well, could something be wrong with the instrument? To make that determination, we went ahead and dispatched himself and a Road Vista technical person, and they went out to the site. They took with them a brand new handheld and a brand new mobile unit. They measured, they compared, and they confirmed. They confirmed that our assessment matched the contractor's. What we discovered was the Epsilon effect. So there's two caveats or two areas I want to talk about before we get into the specifics of the Epsilon effect. First is that I want to address that the relevant issue I want to address here is we're a statistically driven industry in a statistically driven world. From crash modification factors to minimum retroreflective values, we measure and manage our results with ratios or percentages and numbers. But we need to remind ourselves of the people and purpose behind those numbers. We monitor and manage pavement markings because we know how important their role is in a safe guidance and use of our roadways. Retroreflectivity is the primary source of nighttime visibility of those markings. So the purpose of monitoring and managing retroreflectivity is not for the sake of the numbers themselves, but for the sake of roads being safer for the people behind those numbers, our fathers, our mothers, our sisters, and our brothers. Sorry, that's the answer that comes out in me. Setting standards. Well, like any other similar standard, our intention is to create a testing method, as I was talking about earlier, that's relevant to those they affect, in this case, the motorist. But at the same time, we're limited by environmental variations such as different people, different cars, different roadways. And then we also have what technology is available. And that plays a big key in how we do a specification. So the development of retroreflectivity testing methods and standards needed to be created considering the viewing distance and angles, which we're going to talk about, that best represented the motorist point of view. But then we had to marry these with the limitations of standardizing an environment or the type of equipment, the technology that was available. Retroreflectivity measurement testing methods are initially based on the most accessible economic technology, and that was handhelds. So when we designed these specifications, you're going to see where it's kind of, some of it doesn't make sense when we talk about these specifications, but the reason is because we were limited by the technology we had at the time. These constrained testing methods combined with environmental variations and technology changes, they all contribute to what we're going to talk about, which is the Epsilon effect. So the epsilon effect, to understand the epsilon effect, there's a little prerequisite here. First of all, is just to kind of better understand how we measure retroreflectivity. So put your thinking caps on, but don't worry too much. I'll walk you through it. So when we look at measuring retroreflectivity of pavement markings, we consider 4 primary angles. The first is called the alpha angle. The alpha angle is also called an observation angle. The other 3, the beta 1, beta 2, and epsilon, the namesake of this particular study, are all called entrance angles. So let's take a little closer look at the angle. So this is an alpha angle. So the alpha angle, again, is the observation angle, and this is assumed by this diagram. You can see this is the assumed angle between the light source, the vehicle's headlights, and the detector. We call that the detector, which is the person's or motor size, and this is usually assumed at 1.05 degrees. Then we have the beta angle. This is the up and down angle. This is the angle of the object or marking. There you go. Up to the light source, the vehicle's headlights. And this is assumed at 1.24 degrees. Then there's the beta 2 angle. This is the left-right angle. This is the angle between the object or marking across to the light source and detector of the motor size. This is assumed at 0 degrees. I'm going to let you look at this for a moment. Again, this is assumed at 0 degrees. We'll come back to that. Then there is the epsilon angle. This is the tilt slope angle. And this is assumed at 0 degrees. What it is, it's the angle or the object of the marking slope in comparison to the slope of the detector or the motor size. What angle is the object versus what tilt angle or slope angle is the person. This, again, like the beta 2, is assumed at 0. So for a quick review for your test, the beta 1 angle is the up and down angle. The beta 2 is the left-right angle. Oops. The beta 2, there you go, is the left-right angle. And the epsilon angle is the tilt. All of those last 2 assumed at 0 degrees. So let me emphasize the last 2. Remember, I mentioned the limitation of the testing methods caused by available technology. The assumed 0 degrees of these angles were based on the limitation of handheld retroreflectometers. In order for them to operate, they needed to sit directly on the line, causing these measurement testing angles to be set at 0. All right, now we're ready to define the epsilon effect. Now I want to tell you, this is pretty text heavy. I don't normally like to have this much text that you're going to see following in a presentation like this. But the real reason is so that this can be printed off and explained, it almost used as a printed document. And that's the purpose of doing this. So let's see, the epsilon effect occurs when the markings are applied on the left and right side of the roadway's crown or cross slope that has an excessive gradient. This application results in the left center line of the pavement marking to tilt or slope away from the driver, degrading its visibility. The 2 lines are on different epsilon planes or slopes. So one's tilted one way, one's tilted the other. The right center line is normally on the same epsilon plane or slope as the vehicle traveling on the lane and the related detector or motor size. However, the left center line is on a different and even opposite epsilon plane or slope, sloping down and away from the detector or the motor size. What this does is it disrupts the set of angles of measurement. All right, so what have we discovered about the epsilon effect? First, let's look at the field discoveries. We use 2 of the leading mobile and handheld retroreflectometers in the United States, the Road Vista units and the Delta units. maybe I should say it like this, the road vista units and the delta units. There you go. Field, that's my plug. Field initial findings. So what we found was that the handheld instruments did not detect the epsilon effect. Similar to what we found when we went out there and did that initial test, what the contractor found. The left and right center lines measured more equally. But why? Well, they measured more equally simply because the handheld instrument is placed directly on the surface of the line. Therefore, it's always in the same position or same epsilon or slope plane as the marking that it's measuring. However, mobile and lab instruments detected this epsilon effect. The left center line measures less than the right center line. Why? Simply, the mobile instruments measured or scanned the lines on the epsilon plane more similar to the vehicle and the motor's point of view. So as it was scanning across, it was almost skipping over that left line, or that not really skipping, it was hitting it, but but in that angle, it was just as someone would see it if they were driving down the road. So then we went to the lab and we said, okay, let's try this in the lab and find out what we get. So we used a white flat tape. We used a white structured tape, M247 structured tape. We also used a yellow flat tape. And in doing this, we looked at the change that we focused on two things. On the beta 2 angle, remember both of these are supposed to be at 0, but we know that really in the field, both with a mobile retroreflectometer and with a human driver, a motorist, you won't be at 0. So, but we wanted to mess with these and see what the difference was in these. So what we did was we increase in the epsilon variance increased the retroreflectivity variance. The increase of the line's angle toward the vehicle also increased the retroreflectivity. So here again, if the epsilon was changed, if the crown was, the larger the crown was, the more variance there was between the two lines. And what's interesting is if there wasn't a crown and both kind of tilted, if you had one that tilted toward the vehicle versus tilting away, of course, it actually created a higher retroreflectivity number. Decrease in the beta angle equals a decrease in the retroreflectivity variance. So as the vehicle would get closer to the line, it actually went, the change, or the variance went lower, and we're going to show you some graphs here in a second. Beta 2 angle at 0 was a near nil retroreflective variance. So the epsilon effect was overcome by getting closer to the line. The further you were from the line, and you can just imagine how this thing, how the angle keeps going. If you're further away, that it's going to affect that far more than if you're right on top of the line. Structures or profiled markings were less affected by the epsilon variance, and of course that's the reason of that is because they were structured. They were raised above the ground, and so the laser and the human eye are able to catch that reflectivity off the top of those structures. Here's some tables that we have, or some graphs. You can see that that there was as much as when the vehicle was furthest from the line, and you had the greatest epsilon change, a slope difference, it was up to 17% difference in retroreflectivity. And then you go to all the way to the other, where you have the beta 2 is at 0 degrees, means we're right on top of the line, and the variance, even with it as great as it was, as great as we could increase that epsilon difference, we were able to have really very little. It was 0.5% average difference, which is pretty low. So we saw it go from 17.5 all the way down to 0. So why are these environmental variances? Why do they even exist? Well, basically, here's something from TxDOT, because that's where we were working. They said normally it's a 2% grade. However, if it's high rainfall, steeper cross slopes, you can use AASHTO's chart. Well, AASHTO's chart goes from 1.5 to a 6% grade. Now, 1.2% is only a 1.15 degrees. That's a 4% variance. But when you go to 6%, that's 3.4 degrees, which can cause a 10+% variance in your right and left line in retroreflectivity. So what are the countermeasures? First of all, be aware of the issue. When you go out there and you stripe or when you're measuring, you need to know that this issue exists. And also know that the higher the crown, the greater the impact on retroreflectivity. The greater the beta 2 angle, the further from the line, the greater the impact of the retroreflectivity. We do not suggest to reduce the crowns below 2 degrees, obviously, because they're built there for a reason. They're engineered there, and quite frankly, we have no control over that. There is a need for drainage and so forth. Making the left center line minimum higher than the right. Now that's a dog chasing its tail. The brighter you make the left center line one way, the brighter the right center line is going to be coming the other way. So that's not going to solve the problem. We don't recommend or require measurements of these lines to be done with only handheld, because just what I said a moment ago, the reason that we use mobile is for the safety of the workers and the efficiency. You know, mobile measurements provide a much safer operation than a handheld, than standing out in the middle of the roadway. Also, something to consider is that the mobile is actually measuring what we see. It's more accurately measuring what we see as motorists. So by putting a handheld on there, that's not really going to do ultimately the favor of what that spec was designed for, which was the people behind the wheel. We do not suggest adjusting the equipment to measure the levels we want. I know that sounds funny or sounds ridiculous, but don't do it. We need to stay to where it's relative to the motorist. Suggested. What I do suggest, or what we suggest, is use higher crowns only when absolutely necessary. Again, we don't have any control over that, but that's going to be something that needs to be considered. Ensure that the center line markings are well above minimum, 25%. You saw the one was, I think, 17% was the biggest variance that we had, or the biggest average variance we had. Don't be installing markings at near minimum levels, if at all possible, so that if you blow it away, then it's not going to matter that it's different anyway. Measure one direction, one line at a time. This is going to significantly reduce your efficiency, not as much as using a handheld, but you could measure just the line that is on the side of the traffic that the direction you're traveling. Place a mobile directly on top of the lines. Well, that's a pretty easy fix, good fix, because remember, as you got closer to the line, the Epsilon effect wasn't as big of a deal. They measured more consistently across the two lines. But understand that this is probably going to require some type of escort vehicle or a lane closure, which we certainly don't want to do with mobile retroreflectivity or mobile assessment. And you understand that you've got you know, anywhere between an $80,000 and a $200,000 piece of equipment hanging off the side of your car, and you want to make sure that you protect that equipment as much as possible. So driving on top of the line is not always a thing that is good. Here's my thoughts, and this is for what it's worth. Be aware of the situation again. Don't install markings near minimum levels. Position the MRU close to the line as safely possible. Consider an escort. Keep in mind the people behind the numbers. Ultimately, this is so important. Again, just understand that you're not just trying to hit a minimum to get paid, but you're also trying to hit a minimum to best represent or best support the safety of the people behind the wheels. And know that the mobile is more comparable to what the motorists to see. And then, of course, you know, if I was a academia testing agency or something, I would tell you this anyway. More testing should be done on this, but this is the results that we have found.